Okay, guys. So this is, if you're following along, these are, in 5.4, there are a few examples. Okay, so number one. So you've got this ramp. We're going to. Number one, it doesn't even matter if it's frictionless or not because the answer would still be the same. So theta is not fixed. Okay, so number one is saying by changing theta, what are the minimum and maximum accelerations that the system could experience? You can solve this without any calculus. It's a little bit of logic. All right, so how could you minimize the acceleration?
Make that at 90 degrees and then just hanging on the
Yeah, if you make it a 90-degree angle, then you just got two equal masses hanging on either side of a pulley. What's their acceleration going to be? Zero. Good? All right. Follow? All right. Now, what's the maximum acceleration you could experience?
Flat.
If it's flat, and I'm going to come back to that. So if we assume that it's flat, then you're just looking at this. You've got, oops. If you assume that theta is zero, then you've just got this, right?
Yeah. It's just mass, and it's just the one mass.
So let me pause there. You said, huh? Doc? Oh, we'll do slope down in a second. Yep. All right, guys, knock it off. All right, are we good?
Yeah.
So what would the acceleration be in this case? Well, let's see. We'd have a net force of mg, right? Over here, I'd have gravity and normal force. Those cancel out. We're happy, right? So the acceleration of the system would be the net force of the system divided by the mass of the system, which is, our net force is mg. The mass of the system is 2m, and you get that, right? Just g over 2, right? Okay. Now, the question is worded crappily, because it doesn't give you a range for what theta is. All right? So,
Negative 90 degrees and then it's just free falling.
good. Yeah, so then if you assume that instead of it being sloped uphill, it slopes downhill. If you slope it at 90 degrees, then you've just got two things falling, and then your acceleration is 9.8, right?
Yeah.
Okay? Does that make sense? All right. What's the maximum and minimum tension that you could have in the ropes? So if they're both falling, what's the tension in the rope? Zero. Pause on that for a minute. Does that make sense? Why, if they're both falling, why the tension has to be zero?
Same acceleration.
Because your block on the bottom has gravity pulling it down. It's in free fall. So if there's any tension, it wouldn't be in free fall, right? So that tension has to be zero. Otherwise, the block up top is somehow slowing down the block on the bottom. Make sense?
Yep.
Okay. Cool. What's the maximum tension you could have? mg, right? Good? It tells you that the two masses are equal. So m plus m is 2m. Good? All right, everybody good with that? All right, so it says if we assume the ramp is frictionless, what angle would result in an acceleration of 0.25 g? So here we actually have to do some calculations. So, was I too hand-wavy with that first part? Are we good?
Sound good.
You guys got to ask questions if you got them. Okay. All right, so ramp is frictionless. We want the acceleration to be 0.25 g. So what are the forces that are going to affect the motion of the system? Well, you guys tell me. What are the external forces that are going to affect the motion of the system? Gravity. Be more specific. Force of gravity on M2, which we can just call mg, right? What else? The gravity on M1, but I really only care about
Force gravity parallel.
the parallel component, right?
Yes.
So this is mg sine theta, right? That's the parallel component, right?
Yes.
Do I need to worry about any other forces?
Is it frictionless?
It's frictionless.
Oh, yeah.
Perpendicular and normal force cancel out. Good?
Yep.
And so we want to find at what angle our acceleration is 0.25 g, right? So we know the acceleration, we know all of our forces, so we just got to solve for theta. So net force equals net force, right? So let's see, our net force is going to be mass times acceleration, right? So what's my mass, you guys?
Oh, 2M.
2m, because our system
Yep.
is this amorphous blob, right? So 2m times our acceleration of 0.25 g equals our net force, which is mg minus mg sine theta.
Oh, because the other mass is pulling it down. And if there were friction.
Yeah, and if there was friction, well, you guys tell me. Assuming these two masses are equal, without friction, it's going to go this way, right? Like that way. So which way would your friction go? The left, right? Good?
Oh, because it's
Everybody good or no? Does everybody understand why I subtracted the mg sine theta? 'Cause that's the force that's going in our negative direction.
yes.
Okay. All right, so let's solve this thing. Let's see. So my m's all cancel. My g's all cancel. So I'm now looking at this equation. Let's see. 2 times 0.5 is 0.5 equals 1 minus the sine of theta. Subtract 1, and you get negative 0.5 equals negative sine theta. 0.5 equals sine of theta. 30 degrees equals theta. Make sense?
Yep.
Okay. So here's, I think, the only thing that is different here from what you've seen before is that in terms of gravity, it's just the parallel component of gravity that affects the system. Okay? Other than that, it's basically business as usual, okay? Do you guys agree we could now find the tension? And all right, let's try another one. Let's see what's next. So I think this one is the same, but I put in coefficients of friction. Oh, and I changed my masses. All right, so let's do it.
Obviously, pancakes are.
Incorrect. Incorrect. No.
Waffles have little cups to hold all the syrup.
They got little nooks and crannies, don't they? What do you put in those nooks and crannies? Ice cream? Chocolate? Whatever you want. How many nooks and crannies are in a pancake? None. Wrong. Have finest, Brendan. All right.
Better than Eggo waffles.
My waffles are always.
All right. I'm very passionate about waffles. All right, here we go.
You don't have Belgian shake, they should be, Brendan.
All right, here we go. So, let's, instead of using M1, let's just use M. Fair? So we're going to call M1 M, and M2 will be 5M. Cool?
Sure.
So M, and then 5M. So, force of gravity here is 5 mg. Agreed? Notice I'm always starting with the system. This one is actually almost the exact same thing. Do we need to go? Yeah.
Wouldn't it mean that mass 1 is 5 times the size of mass 2?
Yeah? What's your point?
Yeah.
M, 5M. Thank you for catching that, Justin. That's embarrassing. Sorry about that. M1 is the bigger one, so that one's 5M. I just didn't want to keep writing a whole bunch of 2's. Because I'm lazy. You guys haven't noticed.
So, Mr. Hacker, your rant is recorded. We should submit that to Agile. That'd be better than like the children fighting over the
All right, everybody good? All right, so I'm realizing this one's really similar to the last one, so let's kind of plow through it and just sort of, so you can kind of see what's going on. In fact, yeah, all right, we're almost there. So, all right, so here we go. So this guy is going to have a parallel component that's 5 mg times the sine of 30. Yes? So that's actually 2.5 mg, right?
Yep.
I am unhappy with my use of board space here. Sorry, I know you guys can't do this, but I'm out of room, so I'm doing it. 2.5 mg. All right, now, here's why I wanted to go over this one. What way would the system move without friction? You can't just point down, you guys. Left or right?
left.
Left, right?
Yes.
Because without friction, this one is so much more massive that even though it's on an inclined plane, there's still enough force to pull it this way, right?
Yes.
Correct.
Okay, so it's... Oh, that was... How did I do that? Neat.
Well, there's a lot
Okay.
of friction
I did
with
it.
pulling this.
I'm the one who made
Oh,
it.
did you do that? Oh, okay. All right. So we want this thing to be going down the ramp. So nope, you're good. You're good. You're good. I got it. Watch me go. So it's this,
Actually, I think I might get this.
right? There's more force that way, and it lifts the weight on the other side. Okay. All right. So yes, Sarah.
Okay. Will it always, if the left side is bigger when it's on a ramp, will it always be the mass?
No.
Okay.
It depends on the parallel component of gravity, right? So the reason that, yes, this has more mass, but that's not the determining factor. The determining factor is that the FG parallel on this side is bigger than the force pulling in the other direction. So in other words, 2.5 mg is bigger than mg. Cool? Everybody good? Okay, so what other force do I need to put in my drawing? Friction, point for me. Which way is the friction going to go? Up the ramp, right? Okay, and so that's going to be 5 mg times the cosine of 30 times the coefficient of... Oh, we don't know the coefficient of friction. Times mu. All right. I just did a whole bunch there. Do you guys understand this is my normal force?
Yep.
Fg times the cosine of the angle?
Yep.
And then I multiplied by mu to get my friction? Cool. So now we can just do net force equals net force, right? So I'll set it up and then we'll move on to the next example. So let's see. Which way do we want to make positive? Somebody choose left or right, positive.
Right.
Right is positive. Done. I would have done that different, but that's okay. So let's see. So our net force is going to be, first of all, mass. What's my total mass, you guys?
6M.
6m times our acceleration, which is 0.1 g, equals, let's see, mg plus 5 mg cosine 30 times mu minus 2.5 mg. Let me color code so you can see what I just did there. Mg, force of friction, Fg parallel, Fg parallel. Good? Carly, you good? Everybody good? So the M's and the G's all cancel, and so we know everything in there except for mu and solve for it. Follow? What are the, I don't think I had not planned on going through these, so I don't think I have it worked out. Anybody do it? Anybody work way ahead and figure out what it is?
I got 0.36.
0.36? Anybody? That seems reasonable. Well, Blueberries.
2.1 divided by 5%
Let's see. So what do we got? 0.6 minus 1 plus 2.5 is that, and then divided by 5 times the cosine of 30.
Oh, I gave it to you. This is.
Ooh, I got 0.48, but I did that very quickly.
Yeah, I think that's right.
I got 0.48. Okay, are we good? All right. Oh, cool. I thought I had one more example. All right, good, you guys?
Yeah, good.
All right, I hope that helped. I hope that was enough. So tomorrow, you guys will have time to work on the lab. The 5-4 stuff is due Friday. Let me know how I can help you. I'm around before and after school. We got a test next week, so.
Mr. Hacker, I see where